today's, I'm just going to cover a few topics, and in fact, I might even end early because I don't want to get into stochastic matrices until next class. And so I'm just going to focus on eigenvalue computations today. Start with computing the a to the n, which is the application of the repeated application of a matrix onto some initial vector. I'll talk about what it means, and then the similarity transformation and diagonalization, and then talk about principal eigenvalue, and then finding eigenvalues and some theorem, a good interesting theorem that goes with it. Okay, I guess the properties of eigenvalue. So I wanted to start with the physical meaning of a to the n, where a is this matrix. And so we've, last time I ended with this notion of having the eigenvectors forming an eigenspace. And what happens is that if the vectors are even slightly apart, they're not aligned with each other, they're going to be a basis of a complex, in general, a complex eigenspace. And so any vector can be expressed in terms of that basis vector is going to make it possible to compute a to the n. But we really didn't get into the physical meaning of a to the n. Yeah. Would you like to come up and explain what you're doing? No? Why not? You seem to be quite interested in explaining it to her. You're in the front row. You can see me? Yes? Then I can see you. Remember symmetric transformations? Yeah. If you can see me, I can see you. If you're talking to somebody, I can see that. Don't do it. If you want to talk, go outside. There's plenty of space outside, but not in my class. Okay, so the physical meaning of a to the n is quite important. And it shows up in control theory, which we'll get to in about a few weeks. But what you need to understand is that we can take an arbitrarily complicated path, and if we consider a small enough portion of it, it looks linear. So if you have something that goes like this, which is not linear, if you take a really small portion of it, it looks linear. Okay? If you took any small portion of it, it looks linear. And so what we can therefore do is to express this little step from here to here as a linear transformation. Okay? And that linear transformation could depend, let's say this is, just to put some values on this, let's just say it's a two-dimensional graph of x, and this is y, and so y equals some f of x. Okay? We can usually express y plus delta y as some f of x plus delta x. Okay? And so what we have over here is this delta x over here, and this little thing is delta y. Okay? This is just basic differential calculus. So what's going on is that we can basically write y plus delta y as equal to fx plus f dash x delta x. Okay, this is just the Taylor expansion. Okay, and what we see is that we have this f dash, the first derivative, and it turns out that differential equations that involve first or second order and third order derivatives can all be expressed as linear functions. So, what looks like a, you may think that a linear function has to look like ax plus by, okay, plus cz, but it could also look like this, ax plus bx dot plus cx double dot, right? Using the dot notation for derivatives. So what we're seeing over here is that this is also a linear function. So in the general sense of linearity, which we'll talk about in a bit, we will find that this is a linear transformation as well, okay? Which means that this trajectory, which is a two-dimensional trajectory, and when you take the Taylor expansion, is allowing us to express the way that y moves as a quote-unquote linear function, okay? It's not linear in the sense of this linear, but it's linear in this sense, and we'll specify what that is more precisely. What I'm trying to get to you is this intuition, okay? And so what's going on is that I can take some arbitrary trajectory, and if I can write it in this form, then what happens is that this a to the n then represents, so this matrix A would then represent going from here to here in that trajectory. And then a square means going from here to here. And a cube is going from here to here, and so on and so forth. So the repeated application of A to the initial point really represents for us this, think of it as a simulation of the trajectory going step by step by step, where each step is an infinitesimal. Okay? And that's the whole power of having this repeated transformation. So we take some initial vector, we call initial state vector, x, and we can compute sort of x, let's call it x1. x2 is going to be basically a applied to x1. Okay? And then x3 equals a times a square, a square x1. I'm getting this confused here. A square x1. And in generally speaking, xk, the vector xk after k steps will be the a to the k x1. So what happens then is that we are able to sort of project outwards what's going to happen by applying a over and over and over again. Okay? So the ability to apply a over and over again is very, very important. Okay? To give you again a kind of intuitive understanding of this, let's say this is the share price of some share that you care about, Apple. Okay? And you want to predict what Apple is going to do, let's say even 2 days from now. Okay? Which is probably you can make a lot of money doing that. So if you can represent the share price of Apple as a differential equation in terms of its first derivative and second derivative, all right, then what you can do is you can basically claim that you can predict where the share price will be in terms of those derivatives by repeated application of the transformation matrix A, because A in this case, the transformation matrix, is just telling you what the trajectory is going to be. And so you can see right away that this becomes a kind of important matrix to get right, okay, because you're going to predict the share value and do all your trades based on that. Okay? So I'm trying to just give you this motivation of why we want to do this, and this is because we can express these kinds of things, which include the first and second and general arbitrary derivatives, as what you would think of as linear functions. Okay, any questions about this? Okay, so that's why we care about a to the n. Okay, so now last time I talked about sort of the geometric interpretation of how to do a to the n. So let's just look at this. Let's say that we have some initial vector. Let's start with this. Let's have matrix A, and let's say its eigenvalues or eigenvectors. Let's say its eigenvectors are v1 and v2. Just to keep it simple, we just have two. Now remember, these are families of eigenvectors, so they all are, there's a scalar associated with them. Okay, so it's an infinite family, but these are going to be all related to each other by scalar. So everything that falls in the V1 family is a scalar multiple of anybody else. Okay, so let's say there's some initial vector, I'm calling it so x, and x is going to be written as c1 v1 plus c2 v2, where v1 and v2 are the eigenvectors. Well, I used to do exactly the opposite notation in the text, but it doesn't matter. It's the same thing. So if you look at a to the n, so let's just look at a times x. Ax is the same as a times applied to c1 v1 plus c2 v2, where c1 and c2 are these constants chosen to make x. So x is a linear combination of the eigenvectors, which means that if the vectors span the space, we're going to find some combination of v1 and v2 such that we get x, and I'll show an example how that works. So then ax is this, which can be written as c1a v1 plus c2a v2, right? All I'm doing is expanding it out, and this is just simply expanding this thing out over here. C1, C2 are constants, and now we know that AV1 is the same as lambda 1 V1, where lambda 1 is associated eigenvalue. So we can write this as C1 lambda 1, V1 plus C2 lambda 2 V2. Okay, and so this matrix multiplication or the transformation has been replaced by a pure scaling operation with the value C1 lambda 1. And in general, it's easy to show using induction that a to the n x is going to be nothing more than C1 lambda 1 to the n x1 plus C2 lambda 2 to the n x2. Oh, sorry, V1 and V2. I keep getting these types. Okay. All right, so what I'm doing is that the repeated application of A to the initial vector x is replaced by the linear combination of these two scalar exponents, okay? And that makes life much easier because remember we want to get to here, we want to compute the repeated application of A, but I don't want to do all the matrix multiplications. Instead, what I do is I just figure out the eigenvalues, the eigenvectors, and the corresponding eigenvalues, and then I can just do it kind of trivially, okay? And so I can predict the stock price, presumably. Of course, the hard part is to do this, right? That's sort of difficult. And okay, so all right, so let me do an example here. Actually, there's a homework example that let me just do the homework example first because it's an easy one. So we wanted to compute this one, 1941 to the 10 multiplied by 6 minus 4. So from the previous homework and last time's lecture, we know that the eigenvalues and eigenvectors corresponding to this are the following. So I'm going to just replace it. Let me see. I guess I'll do it here. So please exchange your solutions so we can do this. So the eigenvalues and corresponding eigenvectors are minus 5 and 1 minus 2 over 3. And then and 7, 1, 2 over 3. I'm going to actually leave this up because we're going to use it for the remaining homeworks. So we see right away that this vector is nothing more than 6 times 1 minus 2 over 3. Okay, so this is basically what I've been writing as V1, and this is the constant 6, so it's 6V1. So 1941 to the 10th multiplied by 6 minus 4 is just the same as 6 times minus 5 to the 10 multiplied by 1 minus 2 over 3. Okay, and that's it. That's the answer. So you can see I didn't need to do all this. So anybody who actually multiplied this out 10 times should get a 0, okay, because they just didn't get the point. Okay, so hopefully all of you got it, and and the whole point of this homework was for you to see how this fairly painful calculation of 10th power is actually trivial, and you don't need to compute 5 to the power 10. You can just leave it that way. Okay, but I could even do 100, and computation complexity is just very simple. Just where here 5 to the 100 is trivial, right? Because 100 times log 5 to the 5th or 6th decimal place. That's all you care about. E to the power hundreds or whatever. You can take 10 to the power 100 log 5. You can just do through logs. Whereas computation of this, you can't use logarithms. You're out of luck. Okay. So any questions about this? Yeah. Oh.
Eigenvector. No, that's right.
Why did I choose what?
Choose 2 eigenvectors in general. Why not 3? Why not 1?
Why did I choose 2 eigenvectors? What do you mean by that?
Maybe we have 3 eigenvectors.
Oh, I see. The number of eigenvectors, first of all, there's infinite number of eigenvectors, right? Okay, how many eigenvalues do you have? If the matrix is a size 2 by 2, you can't have more than 2 eigenvalues because the fundamental theorem algebra says that the determinant A minus lambda I is going to be of power 2, right? If it's of power 2, there can be at most 2 roots, and those 2 roots correspond to 2 eigenvalues, and corresponding to each eigenvalue, there's an infinite family of eigenvectors. So since it's a 2 by 2 matrix, I don't have more than kind of 2 eigenvectors. But if I do 3 by 3, there would be more. Okay.
We have one eigenvector.
If you have only one eigenvector, then the matrix is of size 1 by 1, which is essentially a scalar. So this is the simplest non-trivial example. Okay. If the matrix is of size 1, it's a scalar. So then finding the nth power is quite easy. So, why bother? So we don't need matrix algebra for scalars. Okay. So, but, all this power I'm illustrating with 2, but in general, we'll be doing it for, think of the matrix dimension as being 100,000 or a million, because in practice, that's what you actually have, right? So 2 already, 100th power is kind of complicated. Imagine a 100,000 by 100,000 matrix, which is routine, by the way. 100,000 by 100,000 matrix is not something that people are, even, they don't even think about it. It's just pretty trivial to solve, yeah. Okay. Any other questions? So in the latest issue of Communications of ACM, actually, I don't know how many have seen it. If you're not members of ACM, you should probably become members. Student membership is quite cheap. And the magazine, the Communications of ACM, is really worth reading. And the first article on the first page pretty much talks about a breakthrough at CMU about being able to compute for certain matrices the I guess the nth power, I guess the equivalent of that. But they can take a matrices of size 1 billion elements and do it on your desktop computer, do matrix operations on those. So it's a real breakthrough. I didn't read enough of it to understand exactly what the breakthrough was, but this is still a hot topic for people to understand. Okay, any questions so far? Okay, good. So once we do this, I wanted to actually so then I want to give you couple of So the one trick that you need to remember is if A has distinct eigenvalues, okay. In other words, the equation A minus lambda I, okay, equals 0 has distinct roots. Which of course are the eigenvalues, right? If this is true, then life is really good. Okay, life is really good because what happens is that the corresponding eigenvectors for these eigenvalues are going to be forming a linearly independent set. Okay, so this is a very important fact. Okay, so you get in a large matrix, you do this, you figure out the roots. Now, by the way, how do you find out roots? It turns out there are some algorithms for finding roots. You can find the roots of any polynomial using these numerical algorithms. And I'll actually give you some names and so on when we talk about when we go into control theory. But in fact, if you just go on Google and search for root finding, you can go to these websites. You can just type in an arbitrary polynomial. It'll tell you the roots. Okay, so even for very large polynomials. So if you can get this polynomial, the characteristic polynomial of the matrix, you can find the roots. You can find if they're distinct. And if you can do that, and they're distinct, then the eigenvalues form a linearly independent set. So why is it important? Well, if the first, you have to remember again geometrically, remember, let's just take the two-dimensional case. Let's say this is the plane and I had these two vectors, v1 and v2 as being eigenvectors. These form a linearly independent set, okay? Which means that this vector cannot be derived from that vector. It's not a scalar multiple, okay? It's in a different direction. That's what it means. Which means any other vector, okay, any other vector in the plane, no matter where it is, can be expressed as a linear combination of the eigenvectors. Okay, and if you can do that, then computing a to the n is really simple because of this little trick you just saw. You just write the vector as a combination of the eigenvectors, and you can just basically compute it. It's really easy, right? So that's nice. But the other thing you can do, which is what I'm going to get into, okay, and then we'll stop after that, is this notion of the similarity transformation. And or it's also called diagonalization. And I'll tell you what we do as a recipe, and why it works is actually beyond the scope of what I want to cover. So I'm just going to give you the sort of the recipe for it. So basically, if we have distinct eigenvalues, then sufficient but not necessary condition, but it's sufficient okay, so distinct so sufficient condition so A has for A to be diagonalized, and this is not in most spell checkers mostly don't let this pass. Diagonalizable, okay, which means I can make it into a diagonal matrix. So specifically what we do is we compute the matrix X, which is like this. You have the eigenvector V1 here, the eigenvector V2 here, and so on until and eigenvector Vn. So the eigenvectors are written out as column vectors, and because these are linearly independent, we know that this is going to have a basis which is going to be full rank. So it has no redundant information in it, and then this matrix D, which is given by X inverse AX, okay, that's X over there, is going to be a diagonal matrix. Okay, that's going to be a diagonal matrix. And why it is a diagonal matrix? Well, that's what I'm not going to tell you, but this is sort of a fact. Okay, so if you're distinct eigenvalues, you get a diagonal matrix. Okay, I'm going to take a break because I'm running a little bit over, and then after that, I'll do an example to show what that is. Yes?
Has the eigenvalues on the diagonal?
On the main diagonal, correct. That's what the meaning of a diagonal matrix.
So if they have the eigenvectors,
right,
then they have the eigenvalues as well. So why do we calculate like this?
Okay, so the if we know the so let's put it like this. Let me repeat the question is, if you know the eigenvalues, why not just write down the eigenvalues? And the thing is, but to apply the matrix A onto initial vector, right? We need to know what these X and X inverse are, because D equals X inverse AX, right? But what's on the diagonal is not the eigenvalues of A. What's on the diagonal is something else. Okay, when you do the example, you'll see what I mean is that the diagonal elements of D are not the eigenvalues of A. Okay, the diagonal values of D are some things, okay, but it has some other contributions from X inverse and X as well. So yes, if you know the eigenvalues, I mean, you can't just write down D from that directly. You have to do some additional work. I'll show that when I do the example. Okay, so I'm going to continue with diagonalization. And I'll first do an example from here so that you because I have the numbers here, and then I'll do the homework because there I didn't. Yeah, wasn't okay. So what I said was that this particular matrix, the fact is that this matrix D is X inverse AX is diagonal. So let me give you an example from here. So let's say the matrix A is this matrix 4, 6, 12, 4. Again, it's sort of a simple. We can, in the book it goes through this, but we can find that the two eigenvalues are lambda equals 4 plus minus 6 under root 2, and you get this simply by taking the determinant, setting it to 0. It's a polynomial of degree 2, so it has two eigenvalues, and those are exactly 4 plus minus 6 under root 2. And the corresponding eigenvectors are 1 square root 2 and 1 minus square root 2. Okay? And as you can see, the two eigenvalues are distinct. 4 plus minus 6 root 2 are two distinct numbers. And so this gives us the matrix X as this one over here, 1 square root 2, 1 minus square root 2, like so. Okay? And that's just writing out it is exactly what I showed over here, as you can write out the vectors in column format. Okay, so then let's compute the diagonal vector D. So D is given by x inverse AX. And so x inverse, I'm just going to give you what it is. It's basically okay, 1 over minus 2 square root 2 minus square root 2 minus 1 minus square root 2, 1. So okay, this value of x inverse is, there is a formula in the book for how to compute the inverse of a 2 by 2 matrix that you can just kind of plug away. But in general, you can find the inverse by computing, computing the minors and so on and so forth. But let's just say this is what it is. So then A is given by this complicated expression, which is this x inverse. Okay, 1 over minus 2 square root 2. I'm just going to write it out. Minus 1 minus square root 2, 1. That's x inverse. And then you have D. And A is just 4, 6, 12, 4, and then x. And x was 1 square root 2, 1 minus square root 2. Okay? And you can simplify this using just matrix multiplication to find that the diagonal matrix D is given by 4 plus 6 square root 2, 0, 0, 4 minus 6 square root 2. In this case, this is just the eigenvalues of A. Now let me see. Why am I tying myself up? So in general, is that true? Is the diagonalization of A? Okay, I better go back and think about that for a minute. Yeah.
Even if we know all the eigenvalues, we can never know the order in which we have to put it on the diagonal matrix, probably.
No, I have a feeling that I'm missing something here, and I'm not able to think in my feet fast enough to tell you whether it's always going to be the case. Because then Milad's question obviously is true. If I know the eigenvalues, why bother doing all this stuff? I can just.
Know the order in the matrix where we want to put the eigenvalues.
No, the order just depends on how I put it over here, right? And I can always put it in any arbitrary order over here. The order is not specified when I write it down like this. When I compute x, I'm sorry. Where is x? When I do x, I don't tell you the order. This order is going to determine what's going to happen over there. Okay. So, all right. So I'm just going to compute. Sorry, I'm going to go back and reread my textbooks and see whether it's always going to be the case. But nevertheless, it is true that this is a diagonal matrix. Okay. And in this case, it is definitely the eigenvalues. And so we can then compute basically a to the 5, which is what we want to do. We're going to compute the 5th power as basically nothing more than the eigenvectors, which is 1. Okay, so let me just do this over here. So a to the 5 is given by x inverse dx to the power 5, right? And which is going to turn out to be x inverse d to the 5x, okay? Because the way this works out is that, how do we do this? So let's just say to the power 2, x inverse dx to the power 2 is going to be what? X inverse dx, x inverse dx, okay? And then these two cancel out because it's just I, so we get x inverse d square x. And if you generalize that, there's going to be x inverse. So this to the power 5 is going to be this, x inverse d to the power 5x. Okay? And now I know what d is. I know what x inverse is. I know x. And so I can just basically plug it in here, and I get a to the 5 to be this horrible value, which is, I'm not even going to write it down. It's 157,783.99 something. There's some bunch of big numbers. You can look it up. But to do it, it was pretty straightforward. All I had to do was compute d to the 5. Okay, so I think now I can answer your question. In order to find a to the 5, I still need to know x inverse and x. So I mean, I can write down d without having to necessarily go through this computation. But to need a to the 5, I need x inverse and x. So, right? So it presumably, and I'll confirm this, you can just write down d by inspection. But certainly you need x inverse and x. So you need to do that work. And once you do that, then you can compute a to the 5. So you can't just know d to compute a to the 5. You need to know d, and you need to know x inverse and x. Okay? So, yeah, and so you do need to do that. Yes?
D equals x inverse ax should be a to the power 5.
Beg your pardon? Oh,
It should be d.
oh, sorry, yeah. What am I doing over here? Okay, oops. So we have wait a second. Okay, just give me a second over here.
It should be a to the power 5, then x.
Right. Just a minute. What am I doing here? Give me a second here. Okay, so d equals x inverse ax, and right. So yeah, let's just do it this way. Okay. So you're right. D to the k, d to the m equals x inverse a to the m x. Okay. So now let me multiply both sides by x. So x d to the m equals a to the m x, right? And if I post multiply by x inverse, I get x d to the m x inverse equals a to the m. Okay, so I guess what you're saying is I need to flip it around. You're right. So, so that a to the m is given by x d to the m x inverse. Sorry, it's not the way. Yeah. Okay, so who was it who pointed at? So I think I made a mistake in writing it over here. So I need to write x d to the m x inverse, not the other way around. I flipped it around by mistake. But in any case, I still need the x and the x inverse matrices in order to compute a to the m. Okay. So any questions about this? Okay. All right. So what we have over here is finding a to the n and using the similarity transformation. So this is called the similarity transformation, or the diagonalization of A to form D, because once you get D, you can plug this into here, and then you can find A to the m from D to the m, and life is good. Okay, so that's the first point I want to get across. So at this point, I want to just talk about a couple of properties of eigenvalues which are relevant and sort of interesting. So let me leave that up for here. So the first point, sort of everything I've done so far basically says, if I have a matrix A, it's a transformation, I really want to know what A to the m is, first point. Second, if the eigenvalues are distinct, I can diagonalize A. Once I diagonalize it using the similarity transformation, I have a very nice way of computing A to the m. Okay, that's all we've gotten to do so far. Now I want to kind of show a couple of properties about eigenvalues and eigenvectors which make life a bit easier. Okay, so the first one is that if A is square and diagonal, then the eigenvalues are the diagonal elements. And we saw this already last time, so I'm just going to state this. And this comes simply from the expansion of A in terms of the determinant. You know, when you solve the characteristic equation, it's going to look like basically lambda minus aii is going to be, so you're going to have essentially terms of the form lambda minus aii, okay, equals 0. That's going to be the characteristic equation, so you can read it off directly. So that's why we like diagonal matrices. And diagonalization essentially converts any matrix A with distinct eigenvalues into this diagonal matrix. Okay, that's the first fact. The second thing is if A is square and symmetric. Okay, if it's symmetric, I'll explain what that is in just a minute, then its eigenvalues are real. And symmetric just means that any element aij equals aji. So we cannot have a matrix where we have the diagonal elements and everything here is symmetric across the diagonal. So aij and aji are the same. And if it's symmetric, then you can show that all the eigenvalues are going to be real. Okay, so that's a good thing to have. All right, and of course the diagonal elements will need to be real as well, right? If the diagonal elements are complex and it's symmetric, then well, if it's zero, if it's all zeros and symmetric, well, you know, we know the diagonal elements are the eigenvalues, so diagonal elements are real. Okay, then this other thing is called the I don't know how to pronounce this. I'll write it down. Maybe one of you can tell me what the right Gerachgorin. How do you pronounce this? Gershgorin. Hershon. I thought it was Hershon. Does anybody have any idea? No? Okay, we'll just call it the G circle theorem. It's a circular sort of and what it says is like this. Let's take any matrix, okay, and let's say the elements are complex. Then what we do is that we take the diagonal elements, which are going to be aii, okay, and we look at the magnitudes of the other elements over here. So this is a11 actually. This is a12 all the way to a1n. So let's just look at that. So for a complex number, which is written on the form, let's say x plus iy, okay, the magnitude is given by, written as x plus iy, okay, equals square root of x squared plus y squared. And the geometric interpretation is that x plus iy is somewhere over here. This is x, this is y, this is x plus iy. And you know, this is sort of a circle, and this distance from the center of the circle, the origin, is the magnitude. It's x squared plus y squared. So we take the sum of the magnitudes of a1j. So j equals 2 to n, okay? And we take the magnitudes of these elements over here. Let's call that some value r. Then we can say that the eigenvalue, okay, the eigenvalues for this lie in a circle on the complex plane, lie in a circle of the complex plane centered at a11 and with radius r, okay? Somewhere there is where the eigenvalues are going to lie. And the same thing is true for each of the other diagonal elements, a22, a23, and so on until a(n)n, okay? So we can take each of these diagonal elements and view them as centers of disks, okay, or circles in the complex plane. And okay, we're going to have sort of these things over here. And the eigenvalues are going to lie somewhere inside those disks. Okay, that's the so-called circle theorem. And intuitively what's going on is this. Let's say that it's a diagonal matrix. If it's a diagonal matrix, we know that all the off-diagonal elements are 0, right? All the off-diagonal elements are 0. So we kind of have this degenerate case of a disk, which is just the point over here. And so the eigenvalue obviously lies right here at this point, okay? As we add more non-diagonal elements, as we expand it, what happens is that the space in which the elements could, the eigenvalues could lie, as it grows a little bit larger, possibility grows larger, okay? So to the extent that if I show you a matrix, okay, if I show you a matrix where the largest values lie on the diagonal and the off-diagonal elements are small, then I can pretty much tell you where the eigenvalues are going to lie, okay? I can have a pretty good idea where they're going to be, okay? And that's good, because if I have a large matrix, if I have some set of transformations which is going to push all the values towards the center, and if I can invert that transformation, okay, like the similarity transformation was taking this, okay, was making it diagonal, okay. But suppose there's some other transformation which I know. Let's call it. I don't want to tell you what it is just for a moment, where it's not diagonal, but it's sort of diagonalish. All the mass is considered diagonal, and it's invertible transformation. So I take the transformation x, okay. So I'm going to do, let's say, d prime is going to be some y times a, okay. So y inverse ay. Then I can go over here, right? And so when I look at this d prime to the power n, I kind of know what to do, because it looks diagonalish. I kind of know, I can sort of ignore the off-diagonal elements, for example. And so this is the intuition behind the Jordan canonical form. Because remember, to do this, A must have distinct eigenvalues. But suppose it doesn't have distinct eigenvalues. Then what we can show is that there does exist a transformation like this, which is invertible, which takes A and converts it into a form where almost everything is on the diagonal, plus we have some elements which are one above the diagonal, okay, and that's all. So you have matrix which looks like this. We have all these things over here, and then we have some elements just above the diagonal, okay, and that's called the Jordan canonical form. And the Jordan canonical form is not as nice as the diagonal form, because we can't just read off the eigenvalues. But this theorem, the circle theorem, tells us that, yeah, it's good. We can sort of, to first approximation, treat these as being the eigenvalues, even though they aren't. Okay, so we can kind of read off. Again, this is very hand-wavy, and I'm not going to go more into this. But for those of you who are going to be going further down linear algebra, this is where you'll see a lot of Jordan canonical form, what I call the Jordan blocks, and the effect of Jordan blocks on how we compute a to the m. Okay, this is giving you a sense of that. So let me do an example just to just to set this. So let's consider the matrix. Okay, where did I put it now? Okay. I'm shuffling the order around as I teach it, so that makes it a bit, right, here we go. So let's take this matrix over here, 9.1, 0.8, 0.3, 0.8, 5.8, 0.2, 0.2, sorry, 0.3, 0.2, 6.5. So the two things that are going to should strike you right away. One of them is that if I consider the main diagonal, the weight, the magnitudes are mostly in here, 9, 5.8, 6.5, and all the off-diagonal elements don't have that much weight. The magnitudes are not that large. Okay, that's the first thing. Second, it's square symmetric, okay, because we have this relationship over here, 0.3 to 0.3, 0.2 to 0.2. So we know it's symmetric. So if it's square, it's square symmetric, the eigenvalues are real. So we know it has real eigenvalues. And second, we know that the eigenvalues are going to be on these disks with these centers, and of radius what? It's going to be 1.1. This one adds up to a disk of 1.0. This is going to be a disk of 0.5. Okay, so the diagonal values happen to be reals. So in the complex plane, which is this is I and this is going to be the real plane, they actually are on the real axis. So we have 9.1, 5.8, and 6.5. Okay, something like that. And we know that the disk is going to be like this, right? So it's 9.1 of radius 1.1, so it's going to be 8, so something like that. But it can't be in the complex plane. It's got to be in the real plane. So we know that it lies in this interval from here to here. Okay, similarly, it will be a circle of size 1 around 5.8, so it goes from 6.8 to 4.8. So it's in this interval, and this interval over here is going to overlap. So we basically get a bunch of intervals, and we know just from looking at it that all the eigenvalues are going to be real values somewhere in this interval, or in this set of intervals. It turns out to be 2 intervals, okay? And that's really nice, okay? Because computing eigenvalues can be complicated. For this, to solve this, I have to solve the cubic equation, right? I got to solve the cubic equation, but here I don't need to. I can simply kind of tell you this is where the eigenvalues are going to lie. However, I still haven't told you what the eigenvectors are, so I can't do this similarity transformation, so on and so forth. But it's kind of nice. I can show you a matrix and say, where do they lie? Here they are. You know, it's a kind of a good party trick. So if you go to a grad student party, you can say, I can tell you the eigenvalues where they lie of this matrix, where they approximately lie. Who knows? Somebody might buy you a beer, for this. It's a math party trick. Okay. So any questions about this? Okay, I want to take a moment to talk about something else, and then we'll look at actually computing eigenvalues for real instead of just talking about it. The next thing I want to talk about, which is related to this, is called the principal eigenvalue or dominant eigenvalue. And again, to introduce this, let me just use this simple example. Let's say that I have some vector v, which I'm writing in terms of the eigenvalues. Let's say I equals 1 to m, ci xi. So what I'm saying is that the eigenvalues, in this case I'm using x to be the eigenvalues. The eigenvalue spans some eigenspace. V is a vector in the eigenspace, with the linear combination ci's given over here. So that's pretty straightforward. The eigenvalues form a linearly independent set, so the basis vector, so they form a basis, and from this basis I have this. Okay, great. So what we're going to do, and so we have some, and of course there's some underlying matrix A that's what's associated with this. Then we can say that A to the n applied to V is equal to A to the n applied. It's applied to this thing over here, sigma I equals 1 to m ci xi bar, and by the fact that ax is lambda x for these eigenvectors, we get the equation that it's going to be sigma I equals 1 to m ci lambda I to the n xi. Okay, so this is what we saw earlier for the case of 2. I just generalized it. But what's interesting here, once you look at it, is that we have the following thing. We have a sum which has only one term that sort of depends on the value of n over here, which is lambda I to the n. Okay, so when we take a bunch of numbers, okay, and we're going to just take the nth power of them, what happens is that, let's just look at this. I'm just going to take lambda, and here I'm going to plot lambda to the n. Basically, it starts at 0 and goes up pretty fast. Okay, so if I'm taking the sum of these n values, ignoring the xi and ci and so on, if I take a sum of these values, I have some value here. Let's say I have lambda this, this, this. These are the 4 values of lambda. These are the 4 magnitudes of the eigenvalues, right? Let's look at the sum. So I have some contribution from here, which is way up there, and that's something, this is, let's just ignore this. There's something from here, and there's something from here. So I got this value, and one all the way up at the ceiling, okay? I don't really care what these values are. Those are all in the rounding error, basically. All I care about is this value over here. I can just pretend these don't exist. They just don't matter, okay? So again, this is the eigenvalue trick, okay? I'm giving you a bunch of eigenvalues, okay? The largest one by magnitude is the only one that really matters, okay? When n is large. When n is small, okay, it doesn't matter. If lambda square, maybe you care about, let's say n equals 10 even, okay? This value of is going to be so large, we don't really care about the rest. So remember from the circle theorem, I kind of know where the eigenvalues are going to lie. And so I can guesstimate where the largest eigenvalue is going to be. Now I can tell you that the behavior of a to the n on any vector v, which can be expressed as this, is dominated by the effect of the principal eigenvalue. Dominant means there's more than one and it has the same value. Remember, once we saw the eigenvalues plus minus I, so they're both equally large. Okay, we're kind of out of luck. But if one is much larger than the others, it's called the principal eigenvalue. This is what it looks like. Okay, and so this gives us now some intuition of what to look at. If we find a matrix where it looks something like this, okay, and we have mostly the mass is concentrated along the diagonals or values, and then this one is the largest value, okay, and all the others are somewhat smaller, then the behavior of this transformation is pretty much dominated by that one large value, okay, because this plus its off diagonal elements is going to be more or less this, okay, and I can kind of guess that the effect of this matrix is going to be dominated by this largest diagonal element, okay. So again, it's intuitive. I'm kind of giving you a sense of things, and all this can be formalized and so on, but you want to understand. So just looking at a matrix, you can say, oh yeah, that element there, that's what's going to dominate everything. Why? Because of the principal eigenvalue. Okay. And there's an example over here which you can go through where I computed I believe the 11th power or something like that, or 10th power, and it turns out that this, the dominant eigenvalues really so much bigger, you don't really care about the other eigenvalues at all. Okay. Any questions about this so far? Okay, so after the break, I'll talk about how to compute eigenvalues, but I want to kind of give you the reason why the principal eigenvalue is so important. When we study graph theory, and we want in this class, it turns out that a graph can be represented by a matrix, the adjacency matrix, and certain graph properties are related to eigenvalues, okay, especially connectivity is related to eigenvalues. And we can say a lot about the graph by looking at its connectivity matrix and the eigenvalues of the connectivity matrix. And in Friday's lecture, we'll see how Google uses this idea to compute PageRank. So it turns out PageRank computation is actually nothing more than eigenvalue computation. Actually computing the dominant eigenvalue is what you want to do. And we'll see how Google does that. At least the early Google algorithm is based on this. So we'll talk about that next time. But today I'll talk about just computing the eigenvalues, dominant eigenvalues. Okay, that was the principal eigenvalue. Let's kind of go on to finding eigenvalues. Oh, and I guess there was a question about what is the circle disk. So I'll just solve that. So the matrix we had was the eigenvalues are 1 minus 2 by 3, 1, 2 by 3. Eigenvectors for the matrix 1, 9, 4, 1. We knew this from before. X is from here. I just left it on. So that's the matrix X is this. So the diagonalization of A is going to be basically X inverse AX, where X is this. So if you just wrote that, that's the answer. You don't really need to sit there and compute the inverse, but you felt like doing it. It's good for you. It builds character, so you perfectly, you should have done it. But this is all you really need, okay, for the solution to the thing. And then the other one was what are the disks corresponding to the matrix 1, 9, 4, 1. And now we can see it's just going to be 1 plus I0, if you want to be really precise, is the center, and the radius is going to be 9. Okay, and the other one is 1 plus I0, and the radius is going to be 4. And if you want to draw it, it's going to be on the x-axis 1. We have basically of radius 4, and then another disk, which is of radius 9. Those are the two disks. And eigenvalues are going to lie somewhere there. If you remember, the eigenvalues of this are minus 5 and 7, and you'll find that minus 5 and 7 both actually lie inside one of the disks. The question?
In the second exercise?
To write down the diagonalization of this matrix 1, 9, 4, 1.
And the answer is just x minus 1?
X inverse AX, where X is this. If you want to, you can go compute it.
Okay, and
what's the actual answer? I don't know. I didn't do it. Does anybody have the answer? 700 minus 1?
Minus 5.
Minus 5. Okay, sure. Those are actually also, oh yes, so maybe I should, this pattern is kind of confusing. This, of course, is the eigenvalues. Okay, yes,
Is that 1 plus I0, that I0 part is important?
No, it's not. Yeah, if you want to be really particular, because the circle theorem is for the complex, then we treat this, but no, this is not necessary. If you just say 1, 9, that's okay, right? Because in the real plane, we don't have circles. We just have intervals, right? Okay.
So the answer is minus 3 to 5 and minus 8 to 10, huh?
Yeah, that's right. You can do that as well. Yeah, this is minus 3 to 5, minus 8 to 10. Yeah, you can do that as well. If you write it either way.
One of them is minus 8 to 10.
Yeah, the union, no, the union is, yeah, minus 8 to 10. That's equally acceptable. It's just the way you represent it, but you just need to understand where the disks are. Yeah. Okay. Yeah.
But it's not symmetric.
No, but if it's not symmetric. Being symmetric is sufficient, but not necessary in this case, right? Just because it's symmetric, if it's symmetric, it will be real. But if it's not symmetric, it may still be real. Right? It's sufficient but not necessary. Okay, let me keep moving on, because I've actually managed to spend more time on this than I wanted. Okay, so how do we find eigenvalues? We can't find all eigenvalues right away, but there are some tricks for computing the dominant eigenvalue. And the most common trick is what's called the power method of computing the eigenvalue. So to approximately compute the dominant eigenvalue of, okay, the method is called the power method for a very simple reason, because we take the powers of A. So what we do is we take the matrix A, which is we want to compute the dominant value of A, and we just take any arbitrary initial vector x0. Arbitrary, just pick anything you want, apply A to it, okay? And then you compute what's called the Rayleigh ratio. And the Rayleigh ratio is given by, let me just write this down, xk ta xk. I'm leaving out the bars over xkt. Okay, so, and if we compute the Rayleigh ratio, then this is going to, and this is the same as, because, okay, and we'll just say x1 equals ax0, so it's nothing more than xt xk plus 1 over xt xk, where, of course, where t means transpose. This ratio is going to converge to the dominant eigenvalue. Okay, that's the kind of the trick. Why does it work this way? It really comes down to the fact that the transformation is taking some arbitrary vector, initial vector, and scaling it up. Right? It's scaling it up by the values lambda 1 and lambda 2, so 2 eigenvalues in 2 dimensions. So let me just write that down. So ax0 is going to be nothing more than c1 lambda 1 v0 plus c2 lambda 2 v1, okay, lambda 2 v2. If the eigenvectors of A are v1 and v2, then applying A to x0, where if the and x0 can be written as c1 v1 plus c2 v2, then ax0 is nothing more than this, right? And a to the m x0 is going to just take these guys and make them to the m, right? We're just going to scale it up. The only thing that matters is this one over here, right? So if you take the ratios of these products xtx, it turns out that that particular thing is going to be scaled mostly by the dominant eigenvalue. So xtx is going to be inflated by this value lambda. So it's going to be pumped up by lambda each time, which is the dominant eigenvalue, and we can ignore the other one. Okay. So let's do the homework example to just kind of give you a sense of what's going on. So here I start with the initial value 1, 1. So if you don't have 1, 1, your answers are going to look a little bit different. But this is A, it's 1, 9, 4, 1. And I just start with 1, 1. And that gives me the vector 10, 5. So this is x0, this is x1. So we just need these two values, xkt, xk plus 1, xk transpose xk. So so we're basically looking at 10, 5 multiplied by 1, 1 over, or actually the other way around. So 1, 1 multiplied by 10, 5 over 1, 1, 1, 1. Okay? And this is 15 over 2 is 7.5. Okay? This is pretty good, because remember the dominant eigenvalue for this was 7, right? 5 is the smaller one. The main one is 7. And with just one simple computation, I just got to 7.5 right away. And if you do it one more time, you should be getting to 6.6 bar. Okay? And yeah, in the interest of time, I'm not going to do it, but it's basically taking 10, 5 and doing it. Well, maybe I'll just show you what happens in the next step. It's really pretty easy to do it. In the next step, we are saying 1, 9, 4, 1 applied to 10, 5 is going to be 55, 45. And then this ratio is going to be given by 100 over 15, which is 6.6. So we're kind of going above and then a little bit below. And if you do it 3 or 4 times, you'll get to 7 pretty quickly. And that's quite nice, you know, and it's showing you how the dominant eigenvalue can be extracted using just this Rayleigh ratio. Okay. So any questions about this? So hopefully most of you got this. Yeah.
Let's say 2, 1 instead of 10, 5.
2, 1, yeah, sure, you can do that. Yeah, that's fine. I mean, that's normalization. I'll talk about normalization in just a minute. Yeah.
How
how many, like if you have this kind of exercise, how many steps do you need to do?
If you do 2 steps at least, if you do more than 2, that's good. But I just did 2 for my solution. Okay, this gives you the dominant eigenvalue. How about the dominant eigenvector? It turns out that we can do that. We can compute the dominant eigenvector as well. And to compute the approximately dominant eigenvector, we need another fact. And that fact is that, again, we use the power method. What we do is that we have to renormalize the eigenvector. So what we do is we rescale or need renormalize. It's another 2 words that people use it. The value of the vector xi, so that maximum element is 1. Okay, if you do this, then xk is the dominant eigenvector. Okay, and that's the dominant vector corresponding to the dominant eigenvalue. So what we're looking for is the vector 1, 2 over 3. Okay, and so let's just. I guess I didn't really ask for that in the homework, but I'll do an example showing that. So let's say we have the matrix 4, 6, 12, 4. Okay, and we're going to have the okay, and so we're going to use the okay. So okay, I'm going to go back to the example 22. Okay, let me start with the initial value 1, 1, and then x1 is going to be just the sum, so it's going to be 10, 16. Okay, so I need to renormalize this, right? Which means I got to make this look like 1, so which is the same as, or which is, I change it to 0.6251. Okay, so that's the renormalization step. Okay, and then using this, we get x2 using this one over here is going to be 4, 6, 12, 4 multiplied by 0.6251, and that gives us the vector 8.5, 11.5. Okay, and 8.5, 11.5, we're going to renormalize this again. And we get over there the vector 0.6961. Okay, this is going to be x2 after renormalization. Okay, so you can see what happens is I'm going to take this value here, plug it in, multiply by the matrix A, and keep doing this. And what happens is that eventually we'll get, after a few steps, we get this to be 0.707 and 1, and which is pretty close to the eigenvalue over here, which is √2, 1. Okay, so we can see that the dominant eigenvector is being extracted pretty closely by using this trick over here. So that is the technique for extracting dominant eigenvalues and dominant eigenvectors. Again, this is only giving you the one value, okay? But in many practical situations, that's the one we really care about. Okay, using dominant eigenvalue, we can roughly guess what the effect of the transformation is on any matrix over here. Okay, one thing you can do as an exercise just to see that you're understanding things is that for the matrix 1941, which has this matrix which has these eigenvalues, eigenvectors, can you get to this eigenvector? How many iterations does it take for you to get to the eigenvector? Basically, it will be 1.66. Okay, how many iterations can you get there? I suspect that in 3-4 iterations, you should probably get fairly close to that. It's kind of just worthwhile trying that out to see how that works. Okay, any questions about this so far? So I'm going to summarize all this by just giving you a little bit more intuition. So we started out with understanding eigenvalues as just being sort of the solution to some equation. Okay, so a matrix is a transformation, and the eigenvalue is a solution to something which tells us that this matrix looks like the multiplication by a constant factor. Okay, that's all we really said. But now we're getting some hidden depths. Okay, and the hidden depths are saying that the transformation can be approximated. Okay, we have transformation on, let's say, a 25-dimensional object. It's going to do something. It's going to actually take the initial vector and scale it and rotate it. Okay, that's what it's going to do. And it's going to do it in some crazy way. However, we can just figure out roughly what it's doing by looking at the dominant eigenvalue. Okay, by looking at the, because of the fact that the multiplication, repeated multiplication, exaggerates the dominant eigenvalue. Okay, so to the extent that we can compute the dominant eigenvalue by inspection, if it's diagonal, or if it's sort of diagonal by looking at the circle theorem and saying this is where the things, where the eigenvalues lie. So the largest eigenvalue is going to be somewhere in this range. If you can ballpark it, we get a ballpark idea of where things are going. Okay, and using the Rayleigh ratio and this normalization, we can quickly iterate to figure out what the values are, what the values of the dominant eigenvalues are. By the way, this Rayleigh ratio is also a trick for you to compute square root of 2. Okay, you can compute the value of square root 2 using Rayleigh ratio quite nicely. And this is another sort of mathematical trick. If you can choose the right matrices, then this ratio is going. If we know, what square root 2 is, we can actually find it using this matrix 4, 6, 12, 4. And so it looks like magic trick. I give you this matrix, I say do these things, and the values of square root 2 keep popping out, okay, from there, which is kind of a nice thing to have. Okay. So that's roughly the intuition. The next class, we're going to go into stochastic matrices, which arise in queuing theory, which we won't go into, but they also arise, as I said, in graphs of various sorts. So this notion of dominant eigenvalue becomes really the basis for web search, which you'll see. Okay, stop here.